We come to our last section in topic 12, which is section 7, continuing to find enthalpy in the very last and final way, which is using bond dissociation energies. So bond dissociation energies are very, very similar to lattice energies, which we learned in topic 5. And so recall, when bonds are made, when two atoms come together and make a bond, energy is released from that process. So in other words, that's an exothermic process. But when you have two atoms already bonded together and you want to break that bond, you have to put energy in. Energy is needed for that, and therefore that's an endothermic process. So remember that. When you want to make a bond, energy is released. When you want to break a bond, you have to need to put energy in. So then we get to the topic of bond enthalpy. Bond enthalpy is an energy change that's associated with a particular bond in 1 mole of gas molecules. We say gas because we need to have a standard. We can't have, sometimes it's gas, sometimes it's liquid. We need to have something standard for the definition. So we just say gas. But it's 1 mole of it bonded together. So it's an energy that's associated with that particular bond. Here's essentially the easiest way to think about it. The higher the bond enthalpy, the stronger that bond, because it takes more energy to break that bond. So bond enthalpies are a measure of how strong a particular bond happens to be. Now, I understand that this image that I have on the screen is pretty small. Okay, you probably can't see that. Maybe you can, I don't know. But if you were to look up, just Google bond enthalpy and then just do a Google image, you would get a lot of different tables that look just like this. So you could do that if you wanted to. But essentially what this table is showing is it's showing various bonds and their bond energies. Okay? And so notice in the table, if you can see it anyway, bond enthalpies are always positive by definition because it just depends what you're doing. Are you making that bond or are you breaking that bond? For example, if I were to look here, this is the very first one. It's the carbon-hydrogen single bond. It's listed as 413 kilojoules per mole. If I'm breaking that bond, if the carbon-hydrogen bond, single bond already exists and I want to break that bond, it's going to take positive 413 kilojoules per mole to do it. Because remember, to break a bond, you have to put that energy in. But if I have carbon and hydrogen separate and I want them to make a single bond, then it's going to release 413 kilojoules for every 1 mole created. So the bond enthalpy is always positive. You have to decide, do we make it positive or negative based on what's happening? Are you making the bond or are you breaking the bond? Okay? So bond enthalpies just tell you how much energy is associated with that bond, and then you make it positive or negative whether or not it's being broken or made. Okay? Let's remind ourselves what happens in a chemical reaction. We talked about this in topic 9, but that's been a while. So let's remind ourselves what happens in a chemical reaction. 3 things happen, and a lot of times they happen very quickly, but three things happen. First of all, your reactants have to break apart, right? All the bonds have to break so that way atoms are able to move around. Well, remember, you have to put energy in to do that. That's an endothermic process. Then the atoms rearrange. That's the second thing. Atoms rearrange. And then finally, atoms are going to form new bonds. And remember, when bonds are made, energy is released. And that is an exothermic process. So there's always an endothermic and exothermic process in a chemical reaction. The question is, which process has a higher amount of energy? In this first picture right here, notice the amount of energy that I put in to break up all the atoms is less than the amount of energy that was released as a result of new bonds being formed. So overall, this reaction right here would be exothermic because overall, there's more energy released than energy that had to be put in. So there's a net loss of energy. On the other hand, this reaction over here, you have to put energy in to break up the atoms. Atoms rearrange, and then energy is released when new bonds are formed. Well, you had to put in more energy than you got out. So as a net total, more energy was absorbed in this reaction. So overall, this would be an endothermic process. That's essentially how you're going to look at these reactions. So using bond dissociation energies, in other words, bond enthalpies, you just need to look, okay, here's the amount of energy I need to put in to break all the bonds, and here's the amount of energy I get out to make new bonds. Based on that, which one's higher, the amount of energy you put in or the amount of energy that's released? That's essentially how we're going to look at these problems. To do so, to find the heat of the reaction, you are going to take the sum of the bond energies for your reactants, and you're going to subtract the sum of the bond energies of your products. Notice this time it's reactants minus products. The reason for that is because, remember, bond energies by nature are positive. There are no negative signs. The sign will fix itself as long as you do reactants minus products, okay? If the bond energies of your reactants is greater than the bond energies of your products, it's going to be endothermic because this is going to end up being a positive value. But if your bond energy for your reactants is less than your bond energy for your products, it'll be exothermic. Don't worry about all of this. Let's look at an example and I'll show you how to think about all of this. Okay, example 24. Using heats of reaction using bond energies, calculate the enthalpy change for the decomposition of nitrogen trichloride. Okay, balance first, because apparently I want you to get some balancing practice, as if you haven't gotten enough this class. Okay, so let's first balance. We need to put a 2 here to balance the nitrogens, and let's put a 3 here to balance the chlorines, and there we go. Everything's balanced. You always want to make sure it's balanced if it isn't already. Okay, since we are using bond energies, we need to actually know what bonds are there. So this is going to be a little bit of a review from topic 6 when we used to do Lewis dot structures, but the good news is you don't have to do a full Lewis dot structure, right? I don't need to know like how many valence electrons are there, what's the shape. I don't need to know that. All I need to know are what bonds are there. That's it. Okay, so to do that, let's look at this. We have NCl3 and you have 2 of them, right? So I need to think about, okay, what does NCl3 look like in a molecule? So nitrogen is going to be my central atom, and you're going to have these 3 chlorines around it. Okay? How do you think the chlorine and the nitrogen are going to be bonded together? Do you think it's going to be single bonds, double bonds, triple bonds? Well, it's going to be a single bond, and for two reasons. Number one, hopefully you remembered from topic 6 that a halogen, when it's in the terminal position, can only have a single bond. That's its only option. The other reason you can figure out that it's got to be a single bond is because notice I have to give you in the problem some information about the bonds. And looky here, I'm giving you the bond energy for a nitrogen-chlorine single bond, right? Is it a nitrogen-nitrogen triple bond? No, that doesn't apply. Chlorine-chlorine single bond? Nope, doesn't apply. The only type of bond I'm giving you for nitrogen and chlorine bonded together is a single bond. So apparently that's how they're bonded together. Now I'm going to draw 2 of them. And the reason why I'm going to draw 2 of them is because of the coefficient of a 2 right there. Okay, these 2 nitrogen trichlorides are going to decompose into, what's the first thing? A nitrogen molecule, one of them. So 2 nitrogens bonded together. How do you think they're bonded together? What kind of bond do you think is going to take place here? Well, considering it's giving me the bond energy of a nitrogen-nitrogen triple bond, I'd imagine that's what bond is going on there. And then plus, what's the other product? 3 chlorine molecules. So how are these chlorines going to be bonded together? These 3 chlorine molecules, how are they going to be bonded together? Well, considering I've given you the bond energy for a chlorine-chlorine single bond, I'd imagine that's how they're going to be bonded together. Okay, the reason why we did that is because now we can understand pictorially what amount of energy is needed to break everything apart and what's the energy that you're going to get out. So the very first thing we need to do is you have this nitrogen-chlorine single bond, right? And you actually have 6 of them. There's 1, there's 2, there's 3, and then there's 4, 5, and 6. So you have 6 nitrogen-chlorine single bonds that you need to break apart, okay? And then what are you going to make? You're going to make a one nitrogen-nitrogen triple bond and 3 chlorine-chlorine single bonds. So using my little equation back here, I'm going to add up all the bond energies for my reactants, and I'm going to subtract all the bond energies for my products. Okay, so what's the total, and I'm going to do it up here because I'm running out of space. What's the total of the bond energies for my reactants? Well, you've got 6 nitrogen chlorine single bonds. So 6 times, what's the bond energy for nitrogen chlorine? It's 200 kilojoules per mole. Okay, and I'm going to subtract, now because that was my reactants, there was only one reactant there. Now I'm going to subtract, what's the total for my products? Well, you've got 1 nitrogen-nitrogen triple bond. So what's that? Triple bond for nitrogen-nitrogen is 945. And like before, I'm not going to write the units just because I'm running out of space. Plus, I have 3 chlorine-chlorine single bonds. 1, 2, 3. So a chlorine-chlorine single bond is 243. Okay, and so let's do the math here and clean these up. 6 times 200, that's going to be 1200 kilojoules per mole. That's the total for my reactants. And I'm going to subtract, what's the total for my products? Well, I got the 945 plus 3 times 243. The total for my my products is 1674. Oh, I got a bug attacking my face. 1674 kilojoules per mole. Okay, so now let's think about this. Let's not get lost in the math. Let's think about this. To break, this is my reactants, right? So I'll put a little R under here and a little P under here to remind myself. The bond energy total for my reactants is 1200 kilojoules. In other words, it takes 1200 kilojoules to go in and break up all the bonds. But as a result, I make new bonds for my products, and that's the total energy that I will release when those new bonds are made. And so I'm putting in 1200 to break everything up, and I'm getting out of it 1674. Right away, you can see you're getting out more energy than you had to put in. So overall, this is going to be an exothermic reaction. So my delta H is going to be negative something. Well, negative what? To figure that out, we do 1200 minus 1674. And that's going to give me negative 474 kilojoules per mole. So that is how I would use bond energies, bond enthalpies, to calculate what the overall delta H would be for the reaction. All right, well that completes not only section 7, but topic 12 and all of Chem 151 lecture content. All right. We'll see you for the review.